Look at the top of the Burj Khalifa. 828 meters of building, and on a windy day, the tip of it is moving. It has to. So the real question isn't how it stands up. The question is, what keeps it calm? Most people assume the hard part of a super tall tower is weight. It isn't, or at least not in the way you'd expect. Concrete is very good at carrying concrete. Stack it, keep it in compression, and gravity is a solvable problem. Wind is the one that gets interesting. Near the ground, air is slowed by everything it has to crawl over: buildings, streets, dunes. Go up, and that friction disappears. The higher you climb, the faster and cleaner the wind moves, and the more leverage it has because it's pushing on a lever arm that gets longer with every floor you add. So a tall tower doesn't fail by being crushed, it fails by being pushed. And long before it would ever be pushed over, it fails a much softer test. The people inside feel it move, and they don't like it. That's the design target, not survival, comfort. Which is why the useful comparison here isn't a column or a tower at all. It's a tree. A tree is the only thing in nature that solves this exact problem at this exact scale. Hold a tall vertical mass steady in moving air on ground that was never asked to carry it. And a tree solves it in two places: below the surface and in the shape of the trunk. Start below the surface, because that's where Dubai makes this difficult. Under the site, you don't find the thing engineers hope for. There's no deep shelf of hard rock waiting to take the load. The ground is a sequence of weak, variable material: calcareous sandstones and siltstones, layered, uneven, and not especially strong. That kills the simplest answer. You can't just drive piles down to bedrock and call it finished, because there's nothing satisfying down there to land on. Whatever you build has to make friction with weak rock do the work. The solution is a piled raft. Two systems working as one. First, the raft. A single reinforced concrete slab under the entire tower, 3.7 meters thick. That slab takes the load from the structure above and spreads it across the whole footprint rather than concentrating it into points. Then, below the raft, the piles. 192 board reinforced concrete piles, each one 1.5 meters across, each one 43 meters long. Look at what that actually is. It's a root system. Not one taproot hunting for something solid, because there's nothing solid to find. Instead, a wide plate and a dense field of shafts, gripping a large volume of mediocre ground and sharing the load between all of it. That's the same trick a tree uses in loose soil. Spread wide, grip everything, let the ground carry the weight collectively instead of asking any single point to be a hero. And this was not assumed. The foundation design was driven by load testing on site and by settlement modeling that predicted how much the tower would sink, and just as importantly, how evenly. A super tall building can tolerate settling. What it cannot tolerate is settling more on one side than the other, because that tilt gets multiplied by every meter of height above it. The roots aren't there to hold the tower up, they're there to keep it level. Now the trunk. In plan, the Burj Khalifa is a Y. 3 wings arranged around a central hexagonal core. That core is the spine, and the 3 wings act as buttresses against it, bracing it from 3 directions at once. The advantage is that wind doesn't get to pick a favorable angle. Push from any direction, and you're pushing against a shape that has structure spread around its center, rather than concentrated on one flat face. Each wing stiffens the core, and the core ties the wings together, so the 3 of them behave as a single connected section instead of 3 separate towers sharing an address. There's a second advantage that has nothing to do with physics. A Y-plan gives you 3 narrow wings, which means daylight reaches deep into every floor. And it gives construction crews a repeatable shape to build over and over. A design that's brilliant and unbuildable is not brilliant. Here's the part that changes how the tower looks. When wind passes a tall object, it doesn't flow smoothly around and rejoin. It sheds. Swirls peel off alternating sides in a steady rhythm, and each one tugs the building sideways. That's vortex shedding. If the rhythm of that tugging lines up with the building's own natural rhythm of movement, the sideways motion builds on itself. That is the force that makes super tall towers uncomfortable. And it's the reason the Burj Khalifa was tested extensively in wind tunnels rather than designed on intuition. The answer is written into the silhouette. As the tower rises, the wings step back in a spiraling sequence. The plan at the bottom is not the plan in the middle, and neither is the plan near the top, which means the wind never gets to establish a rhythm. At every height, it meets a slightly different cross-section, so the vortices that form at one level don't line up with the vortices forming above or below. They shed at different rates, out of step with each other, and the sideways pull gets scattered into noise instead of building into a beat. The tower is doing what a trunk does. It narrows as it rises. It changes profile as it goes, and it presents nothing uniform enough for the air to organize around. The shape isn't decoration. The shape is the wind defense. None of that matters if you can't build it. At this height, ordinary concrete stops being adequate. The walls of the Burj Khalifa use high-performance concrete, with reported strengths in the range of C60 to C80, and the reason is simple. Stronger concrete means thinner walls. Thinner walls mean less weight. Less weight means less load into the raft and the piles below. Everything is connected. The strength of the material sets the thickness of the wall, which sets the weight of the tower, which sets the demand on the foundation. Change one number and every other number moves. Then there's the practical work. Getting that concrete hundreds of meters into the air, placing it in the cooler hours because Dubai's heat affects how it cures, and repeating the cycle floor after floor with enough precision that the tower stays vertical the whole way up. The engineering is the idea. The construction is whether the idea survives contact with a desert. So go back to the top of the tower and to the question we started with. The tip is still moving. It always will be. That was never the failure condition. The Burj Khalifa isn't a solid object standing against the wind. It's a system for moving forces to the places that can absorb them. Weight travels down through the core, into the raft, out through 192 piles, and into ground that was never strong enough to take it in one spot, so it takes it in many. Wind arrives at the top and gets broken up by a shape that refuses to be the same twice. Read it as a monument, and it's a very tall building. Read it as a machine for managing force, and it's a tree with its roots spread wide in weak ground and a trunk that never lets the air settle into a rhythm. It isn't standing still because it's heavy. It's standing still because every part of it is doing a job.